Okay, thank you very much, Dave. Thanks to all the organizers for setting up this online version of the IPAM workshop. And I have never given a mini course of 50 minutes. It will be really mini in the strict sense of the word. Nevertheless, I will try to give an overview of what has happened on classifying and also non-classifying in certain cases actions of groups on von Neumann algebras. And as Stuart in his introduction very clearly pointed out, is that in this work there is like the pre-Cohn and the post-Cohn era. So I think it is appropriate indeed to start with one slide again, putting up Cohn's fundamental classification theorem from the year that I was born, 1976. So stating, first of all, that the hyperfinite to one factor that was introduced in the previous talk is the unique amenable to one factor, or a unique injective to one factor. And one way to realize it is, for instance, as an infinite tensor product of 2 by 2 matrices, as we have just seen. Now, amenability, to make a link with the word mean, one way to characterize this is by the existence of a conditional expectation of B of H onto M, if M is sitting as a von Neumann subalgebra of B of H. And then this really, I mean, usually this would be called maybe injectivity, but this definitely is the variant of an invariant mean on a group. Now, the entire talk will be dealing with the tracial to one setting, but nevertheless, I think that in this workshop, at least that one spot we should say in full detail what, well, full detail, I mean, at least in a complete statement, what the complete classification theorem for amenable factors looks like. So what Cohn proved also in 76, but then was completed with the 3-1 case quite a bit later by Ufo Heuerup, is that amenable factors, they are completely classified by, on the one hand, the type. So the type can be quite a few things. There are the type 1, which are just bounded operators on a Hilbert space of a certain dimension, and that's the n. 2-1 is the case we're interested in with the traces. Then to infinity, where there is an infinite trace. And then there are the more complicated ones, complicated from a certain point of view, that are classified through modular theory for states or weights. And the type is then labeled by a number lambda, which is covering the entire interval from 0 to 1. And then in the 3-0 case, which is somehow the most complex, there is an extra invariant. It's not just the lambda being 0, but there is an extra invariant called the flow of weights. And this flow of weights is an ergodic action of the real line. So there is an ergodic flow that comes as an invariant of the factor. And that makes you wonder about even the nature, what classification means, because of course, ergodic flows are, in many senses of the word, completely unclassifiable. I mean, there is a huge world of ergodic flows, but still, of course, this is a complete classification theorem for amenable factors. Now, having classified all amenable factors, then the next question, as Stuart said, is can we classify their symmetries? And if we want to classify their symmetries, we have to decide what kind of symmetries we will consider, and also to decide classification up to what. And the most obvious kind of symmetries are of course, automorphisms. So if we take an automorphism of alpha, say, of the hyperfinite to one factor R, one obvious way to say that two automorphisms are the same is when they are conjugate. And conjugacy of automorphisms is really conjugacy in the group of all automorphisms, so conjugacy by an automorphism of R. Now, as we will see in a minute, it's much more natural to look at outer conjugacy rather than plain conjugacy of actions. And an automorphism alpha is then considered similar or the same as the conjugated automorphism which are on top of that allowed to be perturbed by a so-called inner automorphism. So every unitary of the hyperfinite one factor defines an inner automorphism adio. And if I consider these two as, say, the same, then we call this classification up to outer conjugacy. Now, in a minute, we will, of course, not restrict ourselves anymore to just single automorphisms of the hyperfinite to one factor, but there will be entire groups of automorphisms, so groups gamma acting on R by automorphisms. And then, but this is not the topic of my talk, although I will give certain hints to that, one can go far beyond that, of course, and start classifying subfactors and view them as quantum symmetries, and then view them as, say, actions of tensor categories on to one factors or on Van Neumann algebras. And actually, but I will not go into that at all, there are many other variants to go beyond group actions. For instance, actions of group OHs on factors, or rather than on fields of factors. Okay, now in order to explain a bit better which type of classification is kind of reachable from this point of view and for group actions, let me already right away say that we will basically never look at classification up to conjugacy for the simple reason that this is completely unwieldy. I mean, it's completely wild, and there are rather all kinds of non-classification statements in that direction. Okay, so what is the correct notion of classification for group actions? Well, that's motivated by looking at their cross product. So if gamma is a free action on the hyperfinite one factor, and freeness here, it's my preferred terminology compared to outer, but it's really the same. I really mean that a non-trivial group element G will act by a so-called outer automorphism. So alpha G is not an inner automorphism if G is not the neutral element. We built the cross product as was explained in the previous talk. And in that cross product, the subalgebra R sits, first of all, as an irreducible subfactor. So the relative commutant of R in M is reduced to just multiples of 1. And this is really because of the freeness of the action. And then secondly, it is a so-called regular inclusion in the sense that by definition, these unitaries coming from the group gamma, they will normalize the subalgebra R. And this normalizer defined in this way, it's a group of unitaries, generates the Van Neumann algebra M. So these are two properties that any cross product has. And then you, of course, immediately wonder whether any irreducible regular inclusion is like this. And it's yes and no. The true answer is no, but it's almost the case. And this will bring me to the key notion of co-cycle actions and co-cycle conjugacy. So what is happening? In the case of a true cross-product inclusion, first of all, you can recover the group gamma from the inclusion by simply noticing that in this context for a free action, the normalizer, it's a group of unitaries. It contains the unitary group of R as a normal subgroup, and the quotient is just gamma. But not only that, it comes with a canonical lift from gamma to the normalizer. I mean, gamma sits as canonical unitaries inside the cross product. Now that's what's lacking in the general setup. So if you take an arbitrary, irreducible, and regular subfactor, so relative commutant trivial and the normalizer generating everything, we can still define this quotient group. And then you can choose a lift from the group back to the normalizer. But the only point is that, of course, there is no guarantee at all that you can choose this lift as a homomorphism. So we will have that UG-UH need not be UGH, but it will only differ by a unitary in R, and that we label as VGH. Now, the reason that I'm putting all this is to bring us to the notion of a co-cycle action and to motivate it. I mean, if I would have just put a definition, it may be a clear definition, but it's not so clear where it comes from. So it really comes from the description of arbitrary, irreducible, regular inclusions. So having chosen this lift, you can define an automorphism of R, I mean, by this formula. And then if you just follow all the notations and definitions, you notice that every alpha G is an automorphism. It's not exactly a group action because the composition of alpha G and alpha H will be alpha GH up to an inner automorphism, namely the one implemented by VGH. And then I will not write the formula here. It's not clarifying. You have to sit down and write it. The VGH, of course, satisfy a natural two-cos cycle property, two-cos cycle formula. Okay, and then there is a notion, the cross-product construction that was explained in the previous talk, can be done in the presence of these cocycles, and then really the original inclusion is the cocycle cross-product inclusion. Okay, so if you see this and if you think of all kind of group theoretic problems, of course, you immediately wonder in which contexts would this two-cocycle obstruction, say, not be there? So are there contexts where like automatically we have this lift? I mean, it's a cohomology vanishing question. And so that's the next thing or the first big problem in this context that I want to sketch. So given such a cocycle action, let's assume this kind of freeness. So every alpha G is an outer automorphism. And then we can phrase the cohomology vanishing problem in different ways. So first of all, really as the two-cocycle being a coboundary. So this is the formula here saying that there exist unitaries so that V, the two-cocycle, is really the coboundary of W, which in this context is given by this formula. Now, this really has a few meanings. So if you have such a coboundary, then perturbing alpha G by at WG, by this inner automorphism, what you get is then an ordinary action. So beta G is now really a group action. And the whole thing of untwisting the cocycle, of making it a coboundary, is then the same thing as writing the original inclusion, the irreducible regular inclusion, as a true cross product without a two-cocycle thing. So that's one question we will be interested in. Is, in certain context, automatically every two-cocycle a coboundary? The second problem we will be looking at is the problem of co-cycle conjugacy. So I was saying on one of the first slides, classification up to what? So we are looking at actions, groups of symmetries of the hyperfinite to one factor, and you wonder up to what you can classify these. Now, the natural notion is co-cycle conjugacy. It looks a bit weird if you see the definition for the first time, but again, it has a very natural context, because when we rather view at cross-product inclusions, or then in general to just subfactors, any inclusion of 2-1 factors, there we all agree, I think, that there is a very natural notion of isomorphism, namely the two inclusions are isomorphic if you find an isomorphism between the large algebras, sending the subalgebra one onto the other. Now, this one, if you translate this properly and do then the tweaks that are necessary to do, what you get is that, and you apply these two cross-product inclusions, it turns out that the natural notion of, say, isomorphism or equivalence between two given free actions of gamma on the hyperfinite to one factor is the notion of co-cycle conjugacy. So what is co-cycle conjugacy? The actions are called co-cycle conjugate if, first of all, there is a one cocycle for the action alpha. So these are unitaries WG satisfying this one cocycle property. The fact that the WG satisfy the one cocycle property guarantees that this perturbed action is again an action. So the formula guarantees that if you look at this thing, that it's again an action of gamma on R. And if that perturbed action is conjugate really by an automorphism to beta, you will say that alpha and beta are co-cycle conjugate. So in formulas, there must exist then an automorphism such that conjugating this one with theta, you get the action beta. Now, this is really essentially the same thing as saying that up to an automorphism of gamma, I know. So essentially the same thing as saying that there is an isomorphism between the cross products, which then restricted to R maps R onto R and actually given by this theta. Okay. So the notion of co-cycle conjugacy, although here it may, if you look at the formulas, it may sound weird. It's very natural because it's really isomorphism of the cross product inclusions. And then the co-cycle conjugacy question is, when are two given actions co-cycle conjugate? And both this cohomology vanishing question and this co-cycle conjugacy question, they are actually extremely hard and subtle questions. So the work of Cohn, Jones, and Ocneanu has been mentioned by Stuart. And so the ultimate result, before I tell what Cohn and Jones did before, is the theorem here by Ocneanu. And so what Ocneanu proved in 85 is if you have an amenable group acting freely on the hyperfinite to one factor, then both the cohomology vanishing problem and the co-cycle conjugacy problem have an extremely neat answer. So the first thing is that whenever you have a free co-cycle action, the V must be a coboundary. So in this context, both amenability of the group and amenability of the to-one factor guarantees that there is never a two-co-cycle obstruction. So every two-co-cycle is a coboundary. And secondly, and this is really an amazing result, is that up to co-cycle conjugacy, there is just one unique action. So all free actions of an amenable group on the hyperfinite to one factor, they are all co-cycle conjugates. Now, there are two other names attached to that. So Alain Cohn did that first for cyclic groups, so both the finite cyclic groups and the group Z. And then for finite groups in general, it was done by von Jones. And in the case of finite groups, but really essentially only for finite groups, you don't need the co-cycle in the co-cycle conjugacy question. There you really get uniqueness up to conjugacy. So I think that if I would have come to IPAM and if we would have gathered and if this would have been a true mini course of several hours or a few hours, I would probably have tried to sketch a proof of how these things go. But I thought that for this survey talk of 50 minutes, I would rather continue on this survey style and actually not go into the proof, but into all kind of related topics. So let me give, because it will be useful for other results later in the talk, just a few constructions of this unique action. Of course, this may sound very silly. I mean, if there is a unique action up to co-cycle conjugacy, there should be only one, yeah? But actually not. The amazing thing is that there are many constructions, and there is no visible way to see why they would be co-cycle conjugate. We just know it from Ocneanu. But so here is the first construction, the so-called Bernoulli action of a group gamma. So you fix a von Neumann algebra with a trace, and let's take k by k matrices with the normalized trace, or take the hyperfinite to one factor itself. So you can then make another copy of the hyperfinite to one factor by taking an infinite tensor product. So in the previous talk, we have seen an infinite tensor product of 2 by 2 matrices. We can do it also with k by k matrices or with R itself. And we can, of course, index the infinite tensor product with the countable group gamma. I mean, that's just coloring the tensor factors. With that difference that now gamma will act by just left shifting the tensor factors. So that's what is called the non-commutative Bernoulli action. Secondly, you can tweak this a little bit and you could stabilize this in the sense that you would take yet another copy of the hyperfinite to one factor and then look at the action alpha G, this Bernoulli action that I defined here. Yeah, I forgot to label this alpha, but this is alpha G, combined with just the identity on R2. So for instance, these two, from an ergodic theory point of view, say they behave quite differently because for this action, you have all the elements in R2 on which the action is trivial. And here there is really nothing where the action is trivial except the scalars. The action is even mixing. So they are by no means conjugate, but yet they are co-cycle conjugate if gamma is amenable, but there is no way to like really see this co-cycle conjugacy. Here is yet another variant that will be nice to illustrate a few other results, the so-called Consciermer Bernoulli actions. So the initial data now is a state on K by K matrices. And if I would take the normalized trace, I would get back to my initial Bernoulli action. But now I take a state, so it's a with a density matrix given by a positive diagonal matrix. You can still do the infinite tensor product construction, except that what you get is no longer a to one factor, but typically a type 3 factor with this product state phi. Now, its centralizer, though, is a to one factor, and it's a copy of the hyperfinite to one factor. And since the shift, still the same shift by left shifting the tensor factors, is preserving the state phi, it will induce an action on this centralizer algebra. So again, we have a nice example of an outer action of gamma on the hyperfinite to one factor. We know that all of these, if gamma is amenable, must be co-cycle conjugate, but you can just not see this, why it would be the case. Okay, let's make a digression to subfactors. So the famous Jones index is given by the Murray von Neumann dimension of, so if n of in M is an inclusion of to one factors, you can look to the n dimension of M, and that is called the Jones index. And we call this a finite index subfactor if the index is finite. Now, this is closely related actually to group actions, because given an action of a group on a to one factor, and given n group elements in gamma, you can build a kind of, one may say, a bit of a silly subfactor, but still, it's a fruitful point of view. The so-called diagonal subfactor, it's the inclusion of n into n by n matrices over n, where you just put alpha GIA along the diagonal. So this is a nice subfactor. And this subfactor actually, in a way, encodes the action. And this is more than just a slogan, because this is really, say, the starting point of the dictionary between viewing finite index subfactors as quantum symmetries and group actions, and why there is so much of a parallel between the two worlds is really because of this point of view. Now, this can be pushed much, much further. So, of course, I will not be talking about a standard invariant of subfactors, but let me nevertheless mention that there is the famous theorem of Sorin Popa, proving that, again, this kind of uniqueness theorem, that for hyperfinite subfactors with an amenable standard invariant, this is really a complete invariant for the subfactor. Now, the reason that I'm stating this here without going into that much further is that, for instance, Sorin Popa's proof for classification of subfactors with amenable standard invariant applied to this diagonal subfactor really gives you a new proof or another proof of Ocneanu's theorem. So there is really content here, yeah? Now, this content actually had, and this subfactor approach to viewing group actions and their classification had led to a very recent advance, actually. So what Popa could prove 2 years ago or 3 years ago now is that this cohomology vanishing result that I mentioned, so Ocneanu's cohomology vanishing of two cocycles, actually holds for actions of amenable groups on arbitrary 2-1 factors. So the group is now still amenable. You look at a free cocycle action now on any 2-1 factor with separable pre-dual, then this V must be a coboundary. So this is a remarkable result. And Sorin introduced this class of called VC, vanishing cohomology. So groups having vanishing cohomology are those groups gamma for which any free cocycle action has the cocycle being a coboundary, so can be perturbed to a genuine action. Now, this is very interesting, and there are many nice open problems around this cohomology vanishing problem, because it's highly unclear how this class VC looks like. Because it's not restricted to amenable groups, because you can do a few easy things. For instance, it's closed under free products. That's almost immediate. If you think of cohomology vanishing as being a problem where you have to lift a quotient map back, of course, if you can do it on gamma 1 and if you can do it on gamma 2, you can do it on the free product. So that is a kind of a trivial observation. With a bit more tweaking, you can actually even amalgamate the free product over a finite subgroup. And that's basically the only thing we know. So on the positive side, these are the only groups that are known to have this cohomology vanishing property. Now, there are quite a few groups known not to have cohomology vanishing. And most notably, Sorin proves that, for instance, property T is an obstruction. I will not go deeply into the definition of property T here, but it's a group theory property. And if your group has an infinite subgroup with a relative property T, then cohomology vanishing cannot hold. Maybe more accessible as a notion, and very group theoretic once more, if a group admits an infinite subgroup that commutes with a non-amenable subgroup, so we say that the group lambda has a non-amenable centralizer, then again, this is an obstruction for cohomology vanishing. So you start feeling that, okay, freeness is maybe not that far afield, but okay, we still have all amenable groups. So there is this speculation of Sorin that this cohomology vanishing question is very much related to the groups being treeable in the sense of measurable group theory, which really is a property of their orbit equivalence relations, allowing certain tree structures on the orbits. Now, this can be seen very nicely, I think, and I wanted to present this. It's elementary, but still, I think it's nice to see this. There is a totally obvious and canonical construction of cocycle actions due to Cohn and Jones. So, and it goes as follows. It's really mimicking the cocycle from the group theoretic context. So if you take a countable group and you write it as the quotient of F infinity of the free group with infinitely many generators, so you choose any surjective group homomorphism, and you define or denote by lambda the kernel of this group homomorphism, then like canonically, you have written the von Neumann algebra of the free group F infinity as a cocycle cross product of this kernel. So the kernel is a subalgebra. Gamma is not sitting as a subgroup because that would need a lift, but you do have a cocycle action. And canonically, you get this kind of picture. Now, if gamma satisfies cohomology vanishing, it means that this lift can be chosen. Of course, it need not be chosen on the group level, but it can be chosen on the 2-1 factor level. And so if gamma satisfies cohomology vanishing, then its group von Neumann algebra must embed into L of F infinity because of this Cohn cocycle. So kind of neatly, if a group satisfies cohomology vanishing, its group von Neumann algebra can be realized as a subfactor of a free group factor. And so, of course, then again, you start feeling that there might be a link to treeability and trees. But first of all, of course, many group von Neumann algebras are known to be non-embeddable into L of F infinity. There are certain properties of L of F infinity, for instance, the Heuerup approximation property, that are inherited by all its subalgebras. The same of not having commuting things. I mean, that's the so-called solidity property of Ozawa. I mean, it's inherited by subalgebras, and therefore it leads to all kinds of obstructions for cohomology vanishing. Now, yet another, but that's extremely wide open as a question, characterizing for which groups L of gamma is embeddable into L of F infinity. There are lots of restrictions, but this is of course extremely challenging. Okay. Now, it's also interesting to note how actually Sorin proved this cohomology vanishing for arbitrary to one factors, because it's through a reduction to the hyperfinite to one factor. And the reduction is via a subfactor proof. So what did Sorin really prove? What he proved was that if you have an amenable group acting with a cocycle action on any to one factor, then actually inside N, you can find a copy of the hyperfinite to one factor on which everything is happening. So what does it mean, everything happening on this copy of R? It means, first of all, that I can perturb my cocycle action with an inner automorphism. So I get this perturbed cocycle action, beta G. Having it perturbed, I change V into a cohomologous cocycle, up to a coboundary given by W. So I can, first of all, perturb alpha G to beta G with the new to cocycle V prime in such a way that beta G globally preserves a copy of the hyperfinite to one factor, and the two cocycle is put entirely inside this copy of the hyperfinite to one factor. This is extremely subtle to realize this, and I found it amazing that it is possible. And then, of course, you can apply Ocneanu's theorem, because I have put everything into a free action on the hyperfinite to one factor, where Ocneanu says that cohomology is vanishing. Now, contrary to the cohomology vanishing question, this kind of property is characterizing amenability. So the only groups that have the property that you can always find invariant copies of the hyperfinite to one factor are really the amenable groups. So that is, say, optimal result. Okay. Let me state a few other, like, say, how to say, single results, standalone kind of results. And one is about one cohomology. So we have seen one cocycles in the definition of co-cycle conjugacy. So a one cocycle, I recall, is a set of unitaries WG satisfying this one cocycle formula here. So one cocycles come with a cohomology relation. So two one cocycles are cohomologous if they are related by a coboundary in this way. And given an infinite amenable group and an action of it and a free action on the hyperfinite to one factor, the space of one cocycles is necessarily huge. Of course, because gamma may act in many, say, different ways, but yet all cocycle conjugate. Now, the fact that this is possible is because there is such a huge supply of one cocycles, because you can have free actions that have very different ergodic theoretic properties, like being compact or being mixing or having invariant elements or not. All of that is preserved by conjugacy, not at all preserved by cocycle conjugacy. And so there is a huge supply of one cocycles in this context. Okay. Nevertheless, what we proved also 2 years ago is that although there is typically a huge supply of one cocycles, nevertheless, they are always approximately inner. They are approximately coboundaries. Now, for actions on the hyperfinite to one factor, of course, this is again Ocneanu. Now, what we proved is that this actually holds for free actions on any to one factor with separable predual. So if you have an amenable group acting, then one cocycles may very well be non-inner, not a coboundary, but they are always approximately a coboundary. And again, this is a property that precisely characterizes amenability. So non-amenable groups don't have this property. Okay, so that was one of these, say, separate results or standalone results that I wanted to present. Since my own work is mainly dealing with the non-amenable setting, let me also show you a few no-go theorems, in the sense that once you leave the amenability on the group side, I mean, lots and lots of things start to be not co-cycle conjugate or not classifiable. And already von Jones actually proved in his paper called A Converse to Ocneanu's Theorem that once the group is non-amenable, there are at least two actions on the hyperfinite to one factor that are not co-cycle conjugate. They are not even outer conjugate. Outer conjugacy is a bit weaker. It's just saying that you can conjugate the one so that the other is to be equal to the other up to an inner automorphism, but you don't require the inner automorphism to satisfy the co-cycle relation. Yeah, but you can read outer conjugacy as co-cycle conjugacy if you prefer. So how did Vaughan actually prove that a non-amenable group must have two actions that are not co-cycle conjugate? It's because he introduced an invariant that distinguishes two of them. And the invariant is a yes-no invariant, very much in the spirit of the property gamma of Murray and Van Neumann. Namely, he was looking at the property, does there exist a central sequence of unitaries that are asymptotically invariant under the group action? So you have it or you don't have it. Now, if the group is non-amenable, this Bernoulli action that I introduced before does not have such approximately invariant central sequences, while its stabilization does have, by construction, by taking the central sequence in R2, such approximately invariant central sequences. So here you have them, two actions, they are not co-cycle conjugate, one's gamma is non-amenable. Actually, this illustrates how neat Ocneanu's theorem is, because that exactly at amenability happens that these two are co-cycle conjugate, and then at non-amenability they are not. I mean, it's kind of amazing. Now, Popa went further, and then for a class of non-amenable groups, again, the ones that we somehow met before. So for instance, if gamma has an infinite normal subgroup with property T, then there must be infinitely many, even uncountably many actions that are not outer conjugate. And the way Sorin did this is by another nice invariant that I think has been a bit overlooked. There is a notion of fundamental group for a free action. And it's very easy to present. So I want to present you the fundamental group of an outer action on the hyperfinite to one factor. And then this can be used as an invariant to distinguish families. So what is this fundamental group? It's actually a source to build co-cycle actions also. So you start with an action on the hyperfinite to one factor or on any to one factor, and you want to somehow scale it with a number t. So you take a number t between 0 and 1, you choose a projection in R with trace t, and then you act on that projection with a group element. So you look at alpha GP. That's a new projection that, of course, has the same trace as SP because the trace is preserved by the action. So since it has the same trace, they are Murray-von Neumann equivalent. So you can pick a partial isometry that links the two projections. And once you have done this, you have created a co-cycle action. Once you have done this, the formula here creates a co-cycle action of the group gamma on this corner PRP. Now, there are no a priori reasons that this co-cycle can be untwisted, for instance. And I introduced it here for t between 0 and 1. You can actually do it for all positive t. And there are choices being made in the story, but a little bit of bookkeeping will show you that it's really well defined up to co-cycle conjugacy. So for every t, I get a co-cycle action alpha t. And here is the fundamental group. You define the fundamental group in the spirit of Neumann as the positive t, for which this co-cycle action is actually outer conjugate to my original alpha. In the same way as the fundamental group of a 2-1 factor would be the positive t for which m to the power t is isomorphic with m. It's always a subgroup of the positive real line, and it's an outer conjugacy invariant for alpha. And more amazingly, it's effective in certain examples. So I presented to you the Consciermer Bernoulli action. So you may have forgotten it by now. So Consciermer Bernoulli was, you take an infinite tensor product of matrices with a state. So the state on the matrix algebra comes with eigenvalues. And in that case, at least if the group is sufficiently rigid, for instance, a property T group, this fundamental group will be the subgroup of R plus generated by the ratios between these eigenvalues. And it's not a coincidence that this is the same as what pops up in, say, these invariants of type 3 factors that you would have in this context, but let's not go into that. So for certain groups, the Consciermer Bernoulli actions have a computable fundamental group, and it can range over all countable subgroups of R plus. So definitely, there are now loads and loads of non-outer conjugate actions for these groups. Now, there is another reason why I'm mentioning this 2001 result by Sorin Popa, because actually this, and it was maybe not getting the right attention back then, this was actually the first deformation rigidity theorem that Sorin Popa proved. Of course, in the 20 years that came after, there have been many deformation rigidity results, and his methods have been applied in wide contexts. And for instance, in a paper that I wrote with, who was then my postdoc, Arnaud Brottier, is that there is a very concrete list, even for any non-amenable group, of uncountably many non-outer conjugate actions of the hyperfinite 2-1 factor. And I will give you the list. So the dichotomy with Ocneanu is completely sharp, yeah? So here is the list. Let's build it. It's a huge list. The list is indexed. Let me first say by what it's indexed. It's indexed by amenable groups, essentially. And we will end up by saying that two actions are outer conjugate, even only if the amenable groups are isomorphic. So it's a huge list. So yeah, for technical reasons, you either restrict to, say, torsion-free groups, or the technical thing is that what you want is that if you have a group with a finite conjugacy class, then that element, if you have an element with a finite conjugacy class, that element must have infinite order. But think of an ICC group, or think of a group with that is torsion-free. And then you can build a copy of the hyperfinite 2-1 factor in this way. It's a Bernoulli action. It's a bit maybe of an involved Bernoulli action. You take an infinite tensor product of 2x2 matrices indexed by lambda. And you also do it once with indexed by gamma times lambda. Lambda shifts this one, also shifts this one. Lambda is amenable, so this is a way to see hyperfinite 2-1, one of our many ways to see it. Now, gamma also shifts. It shifts here. Doesn't do anything here, doesn't do anything to lambda. It creates an outer action of gamma on R. So by Ocneanu, if gamma is amenable, all of them are co-cycle conjugate. If gamma is non-amenable, all of them are different, except when you took, of course, the same group. So this is a quite remarkable dichotomy. Okay. So that's another no-go theorem showing that you cannot go beyond amenability. Now, if you adventure beyond amenability and you go to subfactors, and hopefully this will also happen during this week, I would say that there are basically open problems. I mean, beyond amenability for subfactors, really not much is known. For instance, we don't know which non-amenable standard invariance can come from hyperfinite subfactors. And this is not an anodyne question because we have seen this Bernoulli shift. So any countable group acts freely on the hyperfinite to one factor. So there is no a priori obstruction for all, say, countable standard invariants to act freely on the hyperfinite to one factor. I mean, there is no a priori obstruction, but there is no approach either. And it's even for the most basic example of a non-amenable standard invariant, namely the Temperley-Lipp-Jones one, it's not clear when it can be realized on the hyperfinite to one factor. Now, assuming that you can realize it, so when you have a non-amenable standard invariant acting freely on R, you would then expect, in the spirit of what we have seen before, that then all of a sudden there are like really many of these actions of the standard invariant on R, but also that, I mean, is extremely far out of reach. And essentially the only results we have in that direction are due to the construction of Bijen-Heurup, so which is really like translating group theory properties into subfactors. So if you have a group that happens to be generated by two finite subgroups, so this is just a notation that I use for a group that is generated by two finite subgroups H and K, then whenever you choose an outer action, a free action of that group on R, you can look at a subfactor where you have the H fixed points in R sitting in the cross product with K. Now, this really is like encoding this group. And indeed, you can then show that for this type of standard invariance, you do have like uncountably many realizations of the standard invariant on the hyperfinite to one factor, but there are really not many more results than this one. So that's it for me today. So thank you very much.